Thank you for the opportunity to present our work here. I am Prabhjot and I'll be presenting this paper called Direct Punjabi to English Speech Translation using discrete units on behalf of the other authors for this paper. First, I'll give a little bit of a background of the speech translation area and then define what we tried what the problem statement for our work was and our contribution. Specifically, the model that we created was called unit-to-unit translation. I'll be going over the details of that model and then discuss the experiments we did, results, and conclusion. Starting with the background. So my paper is called, our paper is called Direct Speech-to-Speech Translation. So just to give a background of speech translation, speech translation currently is done in using different subcomponents. So basically there's a pipeline. So first we take the speech in the source language that we want to translate, and we convert that speech to text in that language using speech-to-text model. And then we do machine translation, which converts the text in the source language to text in the target language. And then the final step is converting that text to speech again in the target language. So all of these three subcomponents are usually pre-trained models specifically for speech-to-text, machine translation, and text-to-speech. This performs well. However, there are some limitations. So first of all, because each of these subcomponents are separately trained, they already have some error in them. They're not 100% perfect. So when we use a pipeline, so the error propagates from one model to the next step to the third step. So error propagation is one of the problems with the traditional approach, and of course the inference latency, because we are going through the pipeline, through a number of steps to get to the final result. Secondly, this approach, in order to apply this approach, we have to have the subcomponents available for a specific language that we're interested in. So currently, there are few languages. We have over 7,000 languages worldwide. So there are a few languages that do not have any written form. So they're just spoken languages. So for them, this traditional approach does not work. And also there are some low resource languages, which is the focus of our work as well, for which we don't have pre-trained models for speech-to-text or machine translation or text-to-speech. So that's why this traditional approach is not scalable for building speech translation systems for all of the languages that we have available worldwide. The new approach for speech translation is called direct speech-to-speech translation. So basically here, this approach tries to bypass this pipeline. So we take speech in the source language and we want to convert that speech directly into the speech in the target language without the text. So that's why they're called direct. Now, there are two separate approaches that the authors of the previous papers that I will be referencing here. So this is a newer approach, direct speech-to-speech translation. And the first time this was presented was in 2019. So there are two approaches, the way this is done. So first approach is, so we have a speech. We need to represent speech as a way to make the model understand whatever model we are using to process that speech. So the authors of 2019 paper that first presented this direct speech-to-speech translation, they used spectrograms to represent speech as input to the model. And then the model learned from the examples, and it gave the speech in the target language, which is again given out as a spectrogram. So then the second approach in this area is using another representation of speech called discrete representation, because spectrograms are still high dimensional. So discrete representation is trying to convert that speech to some lower dimensional signal. So here, the approach that this approach was presented by authors of a paper called Direct Speech-to-Speech Translation using discrete units. And this work came out in 2021. So basically here, they still used spectrograms as input for the input speech, but the output in the target language was not a spectrogram, but some other representation of speech called discrete units, which I'll be discussing in the next slide. So before we dive deeper, here is an example of representation of speech. This is not just for speech, but any audio signal can be represented either as a raw waveform or a spectrogram. So we have a raw waveform, which is usually high dimensional. And then we sample this raw waveform by some sampling rate, let's say 16 kilohertz or 48, depending upon what the problem we're solving. And then we try to convert this raw waveform into a sampled signal, or we can convert this raw waveform into a frequency representation called spectrogram, or some other representation. So these are this is normally how audio signals or speech signals are represented. So what we wanted to study was, what if we take the discrete representation of speech? Is that enough to do the translation task? So that's what we wanted to study. And discrete representation is basically, so we have a speech, rather than sampling it using some sampling rate, we use a pre-trained model that learns the sounds from the speech. So each of these numbers here are basically representing some form of sound in the speech. And this is just a sequence of numbers that goes from 0 to 100, and this represents the signal. So what our problem statement is, we wanted to understand if using the discretized speech is enough to represent speech for translation tasks. So as I mentioned before, this approach has been used before. However, nobody has used the source speech. Nobody has used input speech as a discrete speech. So we wanted to explore that. We wanted to understand if we just give discrete representation of the input speech, is that sufficient to learn the translation? So we develop a model and we test that model on a low resource language called Punjabi, and we built a translation model from Punjabi to English. So there are two focuses of our work. One was to just understand whether discrete representation of speech is enough. Secondly, we wanted to contribute to the community to build translation model, specifically focusing on a low resource language. So our contribution is a model which is based on the transformer architecture, and the model, we call it unit-to-unit translation, by unit meaning discrete unit. And we did see that if we use unit-to-unit translation, a model that we developed, it did have a little bit better performance than the previous state-of-the-art model, which is called speech-to-unit translation. So the difference here is we are using discrete unit as input and discrete unit as output. And the state-of-the-art model uses speech or spectrogram representation as input and discrete unit as output. So in order to train the model, we need a parallel speech data set. So we need a data set that contains parallel sentences in the languages of interest, in our case, in Punjabi and English. So that's the data set that we need to train our model. So based on the literature survey that we did, so there are several data sets out there for multilingual data sets like CVSS, all the ones that I mentioned here. And only one of these data sets, called FLURS, has Punjabi and English language pairs. So we could use this data set for our work, but the data size is too small to train our model. So we ended up not using this data set and using something else, which we'll discuss in the next slide. There is an ASR data set called COTPART. This is released by publicly available, and this is released by AI for Bharat. So we used this data set to build our parallel data set for English and Punjabi speech. So COTPART data set contains Punjabi sentences and the text transcript for those sentences. So the first thing that we did was we created parallel English speech and text from this Punjabi data set. And at the end, we had 83,575 sentences, parallel sentences in these two languages. So here, the figure just shows the distribution of the data set. So basically, since we are converting the speech to discrete units, so here the figure just shows the average number of discrete units, which is just the numbers that I showed in the previous slide. So number of discrete units in the data set, that's what's shown here. So we had like average 300 discrete units per sentence in both English and Punjabi. Now, going into the details of the methodology. So this is the overall methodology. It consists of 3 subcomponents or 3 steps. Firstly, we convert speech to units. So we have a raw speech in both source and the target language. And we need to convert this source speech into discrete unit representation or discrete units, which are a sequence of numbers. So this is done using a pre-trained model publicly available. It's called Hubert. So this model is already pre-trained to learn this discrete representation from speech. So we used off-the-shelf model and we passed our speech data and we got the discrete representation. So at the end of first step, we have a parallel data set that contains discrete unit in the source language and discrete unit in the target language. So then this data set is used to train a model, which we call unit-to-unit translation model. So this model is a transformer-based model. So it contains the embedding layer, positional encoding, and transformer encoder and decoder layers. So we use this parallel data set to train this translation model. This training happens in a teacher enforcing manner, which means we use this targets during our training. And when we are training, we are teaching our model to predict the next unit. So we give it all units except the next one that it has to learn to predict. So once we have a trained model, this trained model, what it gives us is the predicted unit. So these are the discrete units in the target language. So now the final step, because we want the speech, so the final step is to convert these predicted units into speech. For that, we use a pre-trained model called vocoder, and vocoder's purpose is basically to convert these units to speech. What I want to highlight here is during the training phase, we convert both target and source speech into discrete units first, and we train the model. But during the inference phase, obviously we don't have this target speech, so we only have the source speech. So that source speech first is converted into this discrete units, and the model predicts the target units, and we convert those units to speech. This is the overall architecture. Before I go to the results, I want to highlight that to decide how many encoder layers and decoder layers we need to use, we did ablation studies. Those are presented in our paper, and in paper we discuss further how many encoder layers, what are the hyperparameters for our transformer model that we used here. Finally, going to the experiments that we did and the results. So firstly, our model is unit-to-unit translation. Basically, this model takes discrete units of the source language, and it gives the discrete units in the target language. And we compared this to the state-of-the-art model that also uses discrete units, but only on the target side, And that model is called speech-to-unit translation. So this takes the source spectrogram, which is spectrogram of the source speech, and it gives out the discrete units of the target speech. And then we also compared our results to a traditional approach, which is, again, a pipeline approach. For that, we used a model called Whisper. And this uses a two-stage approach, which means first the speech is going to be converted into the text using ASR, and then there will be a second component that is going to convert that text from the source language to the target language. So these are the comparisons that we did. And for our method, we basically used the data set that we described before, and we trained our model and we tested our model using the test set, and the BLEU score was 3.9. Now, BLEU score, if we look at the numbers, it's not that great, and we'll talk about like why that might be the case. But if you look at the results from the speech-to-unit translation model, so this is a model that is also publicly available. But in order to use this for comparison, we had to train this model on that same data set that we used to train unit-to-unit translation model. So we trained this off-the-shelf speech-to-unit translation model with our data set, and we tested it on the same test set, and the BLEU score was 0.295. And then the traditional approach that we used was the Whisper model. So Whisper model, again, it's a cascade approach where you have to first go through the ASR, where the source speech is converted into source text, and the machine translation component converts that source text to target text. So one thing I want to highlight is, in order to calculate this BLEU score, I want to explain how we did that. So basically, this unit-to-unit translation and speech-to-unit translation, both of these models, they generate discrete units. So what we get at the end is the sequence of numbers. So first thing that we have to do is convert it into a speech using vocoder. So we used the same vocoder to convert discrete units predicted by unit-to-unit and the discrete units predicted by speech-to-unit. So once we have the speech, now we want to compare the speech to the ground truth. Since there is no standard way or objective way to compare the speech from that is generated here and the ground truth, so what we did was, which is the approach that other papers in this domain have also used. So what we did was, the speech that is generated, we convert that speech to text. So we transcribe the speech first, and then we compare the predicted transcripts to the ground truth, and that's how we calculated the BLEU score. And then I just want to highlight the actual predictions by the model. So this is just a subset of audios. So this is just some audio in the source language, which is Punjabi, and we want to convert that to English. So here, the actual transcript as an example for this speech is Dr. Gurbaksh Singh Frank explains the culture in this way. So this is the ground truth. The prediction by unit-to-unit translation model was actor Gurbaksh Singh brought. So it's not perfect, but it tries to produce the sounds that are similar to what's in the actual speech. And then if we go to the next prediction by the Whisper model, which is the cascade approach, which gives us 18.11, 1136 BLEU score. The prediction by that for the same sentence was, Dr. Gurbaksh Singh Frank describes the practice in this way. So it gets the essence right from what was in the original ground truth. But then the last one is speech-to-unit translation. So here, even though the English is correct, this is necessary to talk about the process of the country, but it does not relate to the ground truth at all. So these are just some examples of the experiments on the test set that we did. In conclusion, through our paper, what we wanted to study was whether using discrete representation of speech for the input language is sufficient to represent speech for translation tasks. So for that, we built a model called unit-to-unit translation model that is based on the transformer architecture. And we experimented on a language pair called Punjabi to English. The BLEU score was 3.9829. Again, it's not great when we compare it to some high resource languages. Let's say we want to go from Spanish to English or French to English. So this is not a good BLEU score, but it is better than using speech to unit translation. I believe that is all I have, so thank you.